going to talk through these two regions questions that you just did as an entrance ticket. So, a suburban high school has a population of 1,376 students. Okay, if I don't have your entrance ticket, please bring it to me now. Thank you. Okay, so that's our total number of students. The number of students who participate in sports is 649. So again with the Venn diagram, one of these is sports. How do I split up the 649? I have no idea yet. The number of students who but I do know, if I label it X and Y again, X plus Y has to be 649. The number of students who participate in music is 433, so that's my other. And again, do I know how 433 is split up? I do not, but I do know that Y plus Z equals 433. And again, if the probability that a student participates in either sports or music is 974 out of 1376, that means 974 kids are total in all three categories, either or both. So X plus Y plus Z equals 974. Okay? So again, if I just add the X plus Y and the Y plus Z, the 649 plus 433 gives me 1082. How much is that over by? Okay, because they're only supposed to add up to 974, but they're adding up to 1082. So 1082 minus 974 tells me we're double counting by 108. So this is 108 in the middle. That means your sports category that was supposed to be a total of 649, you've already accounted for 108 of those, leaving 541. And in the music category, the total was supposed to be 433. Again, you've already accounted for 108 of those. So now we're going to answer the question because the Venn diagram looks good. Actually, the only thing we can do to complete the Venn diagram is our grand total is 974. There's a population of 1376. So 1376 students minus 974 that are already accounted for is going to give us the number of kids that are in neither of these two things, which is 402 outside your circles. Okay? So, what is the probability a student participates in both? That's 108 out of 1376. What is the probability that a student participates in neither? That's 402 out of 1376. Any questions? Okay. Number two, similarly, a Venn diagram is helpful. You've got A and B, and they also tell you what A union B is. So here's A, here's B. I know that A is supposed to be a total of 0.6, I just don't know how it's broken up. So XY and X plus Y is supposed to equal 0.6. For the probability of B, supposed to add up to 0.5, I just don't know how that's going to go, so I have to write it generically that Y plus Z equals 0.5. Now all three of them, A or B, adds up to 0.8, so X plus Y plus Z has to equal 0.8. Already, the X plus Y and the Y plus Z adds up to 1.1, which is over by how much? 0.3. That's your middle section. So that's 0.3. If your total in circle A was supposed to be 0.6, then we have another 0.3 right here. And if our total in circle B was supposed to be 0.5, 0.3, and a 0.2 would make 0.5. And then, so far, 3, 3, and 2 adds up to 0.8, which means 80%, which means that 20%, or 0.2, falls in neither A or B. What is the probability of the intersection? 0.3. Okay, so both similar concepts. All right. So moving on through probability, this is probably today and tomorrow are the two most important days, where I'm saying that because I can almost guarantee something like this is going to be on your regions. Okay? conditional probability. So, first exercise, we're reviewing this same two-way frequency table we saw yesterday. 52 total graduating seniors, and we're trying to take a look at the gender and whether or not they're planning on going to college, okay? So if a person was picked at random, the probability that the person was female, how many females are there, Anthony?
22.
Out of how many total people?
52.
All right, so there's our probability of being female. Probability of going to college, Jake Clancy, what's that?
23. Around 29.
I want the probability, though. I'm not going to walk you through it quite.
29 only 52.
Perfect, okay? Now, here's your intro to conditional probability. There's a new notation that you have to know, and then we got to understand what it's asking us. This is brand new. Part C is asking us for the probability that they are going to college given, and I'll always stress that word, given that they are a female. Here's the notation for that. This is like a straight up and down segment. This is to be read, the probability of going to college given that you are a female. So, it's immediately restricting our population. It's immediately saying, given that you have to be a female. So, now it's out of all the females. Okay? So, this is kind of the other way I would interpret it. Out of all the females, how many are going to college? This is kind of the phrasing that I think of every time. So look at your chart again. How many females are there? 22. So out of those 22 females, how many of those are going to college? 13. Are we on board with that? That's your probability. See how our population has changed? It's no longer out of 52? Because we're only looking at the females, and the question is out of all the females now. So when they say given that they are female, I immediately rethink that, okay, we're now looking out of all of the females. And that changes your denominator, because you're only looking at the female population. And of those 22 females, how many are going to college? Are we on board with that? Okay. To kind of piggyback this with a Venn diagram, the overlap between females that were going to college was 13, so I'd plug a 13 into that overlap. There were a total of 22 females, so 13 and 9 adds up to that total of 22. And there were a total going to college of 29 going to college, so I need 13 and this number to add up to 29, so 13 and 16. Okay? If I were asked this same question via a Venn diagram and I didn't have this two-way frequency chart to look at, but I had to extract this probability from a Venn diagram, are you with me? Okay? I would still ask myself the question, out of all the females, and I would look, how many total females are there? So I'd look in the female circle, there's 22. Out of those 22, how many are also going to college? 13 out of 22. And I would extract that same probability. So you need to be able to answer this kind of probability question, whether the data is presented to you in a Venn diagram, or the data is presented to you in a two-way frequency table, or even worse, the data is presented to you in a paragraph form where you have to build your own frequency table and then answer the question. Are you with me? Okay? So how you actually are going to be presented the information can vary greatly. But once you have it and you have your head wrapped around it, the probability is not that difficult. Okay? Now, D is going to ask us to calculate two things. The probability of someone going to college given that they're a male versus the flip of that, the probability that someone's a male given that they go to college. So let's start with this first one. It's the probability of going to college given that they're a male. So let's start with, we're only looking at the male population. How many males are there? How many males total are there? 30. So out of the 30 males, how many of those 30 males are going to college? 16. So that's up here. So your probability of going to college, if you're a male, let's pretend this is your data in this classroom. If you're a male, your probability of going to college is 16 out of 30, which is just over 50%, but I'll get a decimal for that, 0.53. So if you're a male in this classroom, there's a 53% chance you're going to college, if this was your data, okay? This is going to be different, though, okay? Now the probability that you're a male, given that you go to college, so now we're restricted to, okay, of all the people in the room that are going to college, how many is that? 29, so out of 29. How many of those 29 are male? 16. See how that is going to change the probability. Sometimes it will change it drastically, sometimes it will change it slightly. In this case, it's 55%. So if we know you're going to college, there's a 55% chance that you're a male. Okay? Any questions on conditional probability? And then we'll actually answer the question, which is more likely, that a person picked at random will be going to college given that they are a male, that's this one, or that a person will be male given that they are going to college, that's this one. Which one's more likely? Right, second one. Not very far off though, okay? So I wrote that conditional probability formula. I kind of wrote out in quotations the way I like to think about that, but we already wrote that out up here. So we're going to jump right down to the bottom, which is a Venn diagram given to you, but three-way Venn diagram, so there's the first little twist. And then I'm asking you a bunch of conditional probabilities on this. Okay? So on the first one, cats, birds, and dogs, by the way, so pet owners. What is the probability that you own a cat given that you own a bird? So, we're only restricted to people who own birds. How many is that? How many people fall in this bird circle? 15. 10 plus 2 plus 2 plus 1? So, out of those 15 people, how many also own a cat?
2. 4.
Nope, look at the cat circle.
12.
And look at the bird circle. They're intersecting with the 10 and the 2, so 12 of them. So 12 out of 15. Wow, that's a pretty big percentage. So it's just saying that if someone owns a bird, there's a pretty good chance they also are owning a cat. Okay, and 12 out of 15 is 0.8. Okay? In part B, we flipped it around. So we're looking for the probability of owning a bird given that you owned a cat. So how many cat people are there, Molly? 28. This is my cat. 10, 22 plus 6 is 28. So out of those 28, how many of them, Molly, are also bird people? 12. The same 10 and 2 where cats and birds overlapped before. Not nearly as high as a probability. That's only 0.43. See how drastically they can be different? So just to interpret this, this is saying if you own a bird, there's a really good chance that you'll also own a cat. But if you own a cat, there's not that great of a chance that you're going to own a bird. Okay? Now, we can guess as to why that would be. We can hypothesize why that might be, but at the end of the day, that's not our job. It's just, there seems to be some sort of correlation for bird owners. Why would a bird owner might also want a cat? I don't really know enough about owning these pets to be able to guess as to why this is, but clearly there's something there, right? Something about being a bird owner is making these people want cats. Okay? Seems like torture. Try C on your own. And if you want to move past C, go ahead, but just try C on your own. Austin, give me that. Thank you. Keep working. Keep working. Hey, Morgan, what did you get for C? 4 out of 15. So, out of all the bird owners, what's the probability that one also owns a dog? So, in the bird circle, there are 15, so I like her denominator. And out of all of those 15, how many also own a dog? That's going to be these 4. 4 out of 15. Beautiful. Okay? How about D? Did anyone get to part D? Hunter? 4 out of 19. So out of all the dog owners, 15, 16, 17, 18, 19, how many also own a bird? These 4. Perfect. Okay? Did anyone get E? Sarah? 8 out of 19? So out of all the dog owners, and that is definitely 19, how many also own a cat? 8. Perfect. And the flip of that, Scott?
8 out of 28.
8 out of how many? 28. So out of all the cat owners, which there were 28, how many also own a dog? 8 out of 28. Now, these are pretty low. 8 out of 28. Now this I can hypothesize about because I've owned a dog before. If you own a cat or if you own a dog, why are these percentages pretty low? Why do so few people own both? Yeah, they don't get along. Dogs and cats, from what I've seen, usually just chase each other. My dog's always hated cats, so, and again, that's a hypothesis. And we're going to see whether or not things are related to each other, and we're going to work towards a more conclusive answer as to, are these things independent of each other? Or is there some sort of suggestion that there might be a correlation, and then we can hypothesize about what might cause that correlation? Okay? But do we understand conditional probability, the given, okay, and how to do that? All right. So, frequency chart, a little bit more to it, just an extra category. It's a 3 by 3, so 3 hair colors and 3 eye colors. We're asked the probability that someone has brown eyes given that they have blonde hair. Try that on your own for a minute. Probability of someone having brown eyes given that they have blonde hair. Oh my gosh. Let me see. Let's see this here, Vinny. Easy?
Yes.
Beautiful. Very nice. Good. Margaret, what'd you come up with over there for part A? What'd you say? But what was your fraction before you give me the final answer? Did you have something over something? Where'd you get .10 from? So, blonde hair, brown eyes was .10. So, this probability, Margaret, and anybody else, this is just the probability that by picking someone, you're picking someone who has blonde hair and brown eyes. This does not mean and probability. This is what is the probability that someone has brown eyes given that they have blonde hair. Alyssa, what'd you come up with for your fraction? 0.10 over 0.35. And that's better because the first thing you should look at in the given type of probability, conditional probability, is, okay, so given that someone has blonde hair, look at how many blondes you have, 0.35. So that's the population we're looking at, which is why that's my denominator. So out of that 0.35, what's the probability that someone has brown hair? 0.10 out of 0.35, which 0.1 divided by 0.35 gives me a 29% chance. That's not very high, is it? From your experience, if you have blonde hair, what color are your eyes a lot of times? Blue. So you can see why that might be a little less of a likelihood. Okay? Next one. So Margaret, what would you look at first in this one? Okay, and what is the green eye total? 0.25. So given that you have green eyes, so out of that 0.25, how many of those green-eyed people, Margaret, also have red hair? Perfect. Does that make more sense? Good. And 0.15 out of 0.25 is a 0.6, so a 60% chance. So if I find someone and they tell me they have green eyes and they say, well, guess what color my hair is? Guess what I'm saying? Red. I'm going to guess red because 60% of green-eyed people apparently have red hair as well. So I'm best to guess red. What is that? Green eyes, red hair. Have you ever heard that? Irish. That's what I would think. Yeah, maybe. Okay. So the question then is, does having red hair seem to have some dependence on having green eyes? I would think so. Because if I just take a random person, if I just take a completely random person, what's the probability of having red hair? Look at your chart. Probability of having red hair. What's the probability that people have red hair? Pretty low, right? We don't know a ton of redheads. It's a pretty rare thing. So just having red hair is a 20% chance. But your probability of having red hair, given that you have green eyes, has gotten a significant boost to 60%. So does there seem to be some dependence? Absolutely. There seems to be. Now, we're never going to be able to say that something definitely is dependent on something. It might be a coincidence, but we will definitely say they're clearly not independent of each other. Okay? If they were totally independent variables, like having red hair and being from New York State, those are independent ideas, right? So the probability of having red hair is 20%. The probability of having red hair, given that you're from New York State, probably still going to be around 20%, because those two are completely independent of each other. But when you restricted your population to green-eyed people, and now all of a sudden your probability of having red hair is bumped up to 60%, that suggests that these are not independent. Okay? Yes? If they were completely independent, that probability wouldn't have changed. And that's what's happening down here. This is the conditional probability is critical because you are I'm 90% sure you're going to be asked an independent type question on the regions. And in order to answer an independent type question, you need to be able to compute conditional probability. So just like we did up here, we compared the probability of red hair with the probability of having red hair given green eyes. That's your test for independence, is to have to calculate those two probabilities. So just using A and B, you would compare your probability of B with your probability of B given you're restricted to the A population. Okay? Or backwards. You can compare your probability of A with your probability of A given B. Okay? And they're not going to tell you that that's what you have to calculate for independence. You need to memorize that. Okay? Go ahead and fill in this frequency table with the missing values to the best of your ability. You can't just start anywhere. You've got to only fill in what you're 100% sure of, which will then make you 100% sure of the next thing, and the next thing, and the next thing. Thank you. Chance, what were you able to fill in first?
How many females drove a car?
How many, he filled in this first, because they were all supposed to add up to 92. Good call. What'd you get? 17. And that makes them all add up to 92? I'm trusting you on that?
Yeah.
Okay, perfect. What else? Oh, not to mention, going across with a car, they add up to 45. Okay. Next. What can you fill in? Who filled in something else? Tyler? Which one? The total, which was? Did you get that from here?
Yeah.
221. Now you can go backwards and fill in this, right? What was that? 80. Now you can go backwards and fill in this. What's that?
34.
Awesome. I can do the bus, because these two have to add up to 27. Hold on, don't move. 15. And now this number should work out this way and this way. What is it? 52. Here's your homework. Listen carefully. Finish this. Calculate these 4 probabilities at the bottom based on this chart and the worksheet. Any questions? Goodbye. Have a good day.